All right, this video is intended for a quick review of the concentration of a saturated solution experiment in grade 9 advanced science. In that experiment, you were given a solute, a type of salt. We were using sodium chloride, most of us. Some of you may have used calcium chloride. If you did, I'm going to ask you to delete your data because there was an error with the calcium chloride. So I've given you here some sodium nitrate sample data. So everybody should copy down those numbers into your data table for sodium nitrate. And then everybody should also have some data for sodium chloride. If you did calcium chloride, you should get the data for sodium chloride from a friend. So some quick vocabulary review. In this experiment, the solute was the salt. So sodium chloride, or for some of you, calcium chloride. The solvent was the liquid that we were dissolving the solute in. So for all of us, it was water. We took about 5 grams of the solute, the salt, and we added it to about 5 milliliters of water, the solvent. When we added them into a test tube, at that point, we had a mixture. And the mixture was heterogeneous. It was heterogeneous because at that point, the solution, the salt, was starting to dissolve at the bottom of the test tube, but it was mostly just water above it. So the concentration in the water of the salt was not the same everywhere. It was different. It was greater at the bottom of the test tube than it was at the top. So that's what heterogeneous means. The concentrations are different at different places. We stoppered the test tube and then we shook it vigorously for about 5 minutes. And after 5 minutes, we let the undissolved salt sink to the bottom. Let me just quickly draw for you a test tube here. So at that point, you had some water, you had some undissolved salt at the bottom of the test tube, and then in the water above that undissolved salt, there was dissolved salt all throughout the water, and it was equal concentration everywhere because we had been shaking quite vigorously. Since it's equal concentration everywhere, you now had a homogeneous mixture. A homogeneous mixture is one where the concentration is the same throughout, or where there's the same amount of salt everywhere in the solution, in the mixture. That homogeneous mixture is what a solution is. So this phrase, homogeneous mixture, can actually be rephrased as a solution. A solution definition is a homogeneous mixture. Now, there was undissolved salt at the bottom of our test tube. Why didn't it dissolve? We had shaken the test tube for 5-6 minutes. Why did the salt not all dissolve? The reason is because it had reached its highest possible concentration at 20 degrees Celsius, the temperature in our lab. So at that temperature, the little bit of water we put in the test tube was only able to dissolve a certain amount of salt. At that point, any extra salt just stayed on the bottom of the test tube, undissolved. So the solution that we had at that moment was said to be saturated. It was not able to dissolve any more salt. It had reached its highest possible concentration. That's what a saturated solution is. The purpose of the experiment was to calculate the concentration of that saturated solution. The concentration of a saturated solution is called the solubility of the salt at that temperature. So solubility is the concentration of a saturated solution at a certain temperature. So that's what we're doing in this experiment. So we began by taking an evaporating dish, and you can see a picture of one on the left side of your screen there, and we found its mass. So in my sample data, the empty dish weighed 31.26 grams. Then we took that test tube with the saturated salt solution in it, and here's an important word, we decanted the solution. What that means is we poured the solution into that evaporating dish, but we left any undissolved solid in the test tube. So when you pour the liquid out but you leave the solid behind, that's what decanting is. So we decanted the saturated solution into the evaporating dish. Not a single particle of undissolved salt got in the dish. Then we found the mass again. Now the mass went up. So why did the mass go up? Now it's 36.13 grams. It went up because there's a saturated solution added to the dish. So if we subtract the mass of the dish from the mass of the dish with the solution, the difference must be the mass of the solution that was added. So 36.13 take away 31.26 gives me the mass of the solution. So I get 4.87 grams. For this video to really help, it would be smart if you actually have your own calculator and do the subtraction of the numbers with me and verify that yes, this is what the numbers actually are. If you're just watching, it won't be as helpful. Now, after we had the saturated solution in the evaporating dish, we put a Bunsen burner under it and we began to heat. As we heated, the water that was in our solution evaporated. With less and less water, suddenly there was precipitate of solid salt in the dish. Eventually, the salt became drier and drier. Eventually, there was no visible water left, but it looked pasty. At that point, salt was starting to spit out of the dish. So we took the burner out, we let it cool, we put it back under, and we kept doing that until the salt was as dry as possible. We then let it cool, and we weighed the dish with the salt, the third number in the table up above. The dish with the salt was 33.57 grams. Notice that that was less than the dish with the saturated solution. So why did the mass go down? Well, water escaped. So then the difference between those two numbers must give me the mass of the water that had escaped. But the water that escaped was the water that was in our solution. So it's the mass of water in the solution. So 36.13, take away 33.57, the mass of the dish with the solution minus the mass of the dish with the salt. The difference is the mass of water that was in the solution. So down below, the mass of water was 2.56 grams. Now we need the mass of salt that was in the solution. The salt, well, look at the numbers at the top. The first number is the mass of the dish. The third number is the mass of that dish with the dry salt in it. So if we subtract those numbers, we're going to get the mass of the dry salt. So 33.57, take away 31.26, gives me, whoops, I just added by mistake, 33.57 minus 31.26 gives me 2.31 grams of salt. Now, on your data table, you'd be smart to put a few things on the left-hand side. Where it says mass of saturated solution, remind yourself that a saturated solution is actually water plus salt. The mass of the salt in the solution, we can just call that S, salt. And the mass of water, we can just call W, water. So notice if you take S plus W, 2.31 plus 2.56, you're going to get 4.87, right? The mass of the solution was equal to the mass of the salt plus the mass of the water. Another way to get the mass of water was to take the mass of your solution, 4.87, and subtract the mass of salt that was in the solution, 2.31. Then you could say the mass of water is 2.56. So there's another way to get the mass of water. Now we have the mass of the water, we need its volume. We did this in our last unit, so we could just set up a unit multiplier. I'll take 2.56 grams of water, and I can get rid of grams, and I can switch to milliliters of water. Of course, this is a density calculation, so you look up the density of water, 1.00 grams per milliliter at room temperature, and so 2.56 divided by 1, it's the same number, 2.56 milliliters of water. You now know the mass of salt and you know the volume of the water. So you could calculate the concentration of the saturated solution. Mass of salt divided by the volume of water times 100. So for me, it'll be 2.31 grams, the mass of salt, divided by 2.56 milliliters, the volume of water in the solution, times by 100. That's going to give me 90.2. I'm following my rules for significant digits. 90.2 grams per 100 milliliters. When we multiply by 100, it gives us per 100 milliliters of water. Now the next line of the table says class average. I'm not going to do a class average, so let's cross that out. Let's put the true value. Okay, so the true value for the concentration of the saturated solution. We can get that by looking at our solubility chart at the back of our science booklets. I was just using sodium nitrate, and sodium nitrate has a chemical formula NaNO3, so that's this salt here, NaNO3. So that curve represents sodium nitrate's solubility at different temperatures. And you remember solubility is the same thing as concentration of a saturated solution. We were at room temperature, the temperature in the lab, so we can say at 20 degrees Celsius, that was our lab temperature. So on my chart, I'm just going to go up from 20 degrees until I hit the sodium nitrate curve, and then I can see that its solubility is between 80 and 90. In fact, it's between 85 and 90. In fact, it's just slightly closer to 90, so I'm probably going to say 88 grams per 100 milliliters, the units on the y-axis. So 88 grams per 100 milliliters. You might have said 87. That would be okay as well. So I'm going to say 88 grams per 100 milliliters. That's from my solubility chart. So the 90.2 is my experimental value. The 88 is my true value, so I could calculate the error in my experiment and the percent error as well. Now, one last thing before we go. You could probably think about several sources of error in the experiment, things that might have gone wrong in the experiment that would have affected this result. In my experiment, my solubility, the concentration of the saturated solution, was higher than the true value. So of all the possible things that could have gone wrong, what would have made my result be higher than it should have been? Well, when you look at the formula for concentration, it's essentially a fraction. It's the mass of solute divided by volume of water. So what could have made that fraction larger than it should have been? In a fraction, if you increase your numerator, so in other words, if the mass of my solute were for some reason too big, that would increase my solubility. On the other hand, if the denominator, the number on the bottom, was too small, that would also make the fraction too big. So I have to think of a reason why the mass of solute might have appeared to be too big, or why the volume of water might have appeared to be too small. So of all the things that could have gone wrong, what would have caused either one of those things to happen? That would have been a possible reason why my result was larger than it should have been. All right, so I hope that helps understand how to do the calculations in this experiment. Good luck.